theoretical questions. Did I start a little bit too early? Yeah, okay. So I'm going to tell you today a little bit about some theoretical questions that are kind of mostly about unsupervised and deep machine learning. So just so that we have a little bit of context, among the things that kind of we're most excited about in the recent maybe like 5 years in machine learning is learning using very little labels or maybe completely unlabeled data. And so of course, the first question here is, what does it even mean to learn when you don't have any labels? So this could be something as kind of simple and classical as understanding some structure in the data. So maybe some kind of latent information, maybe some kind of correlations or causal structures. So maybe you can imagine you have a bunch of patients with some symptoms and you want to be able to learn sort of the kind of the causal graph of the symptoms that some diseases cause, or some kind of clustering. It could mean something a lot more complicated. So for instance, maybe you want to learn how to be able to kind of move through the space of faces by kind of conditioning on some complicated distribution. So they have something like this nifty gadget on the bottom left here, or maybe extract some kind of useful features from the data that are then kind of useful for something downstream. So maybe something like, take the lines out of a zebra and put them on a horsey. All right. So there's a kind of bunch of questions that are of theoretical interest here. And so like, just to give you some kind of rough grouping, there's questions of representation. So these would be questions of how expressive a certain model is, how interpretable is it. Then there's questions about inference. So these would be things like asking some learned model some probabilistic queries. So maybe something like the sampling or conditional sampling kind of example that I had on the previous slide. And of course, maybe the most kind of classical question is here are questions about learning. So basically, sort of questions around finding the best fit model from some raw data. So this could be statistical questions, so questions about what's the sample complexity of learning some model, or it could be algorithmic questions. So basically, can you design efficient algorithms to do so? So let me tell you why the theoretical lens is useful here. So in large part, a lot of the questions that we actually want to solve, especially in unsupervised learning, kind of in their cleanest, most kind of like most abstract mathematical formulation, are typically going to lead you to intractable kind of results. And here, intractability could be algorithmic. So basically, it's going to give you problems that are NP hard or sharply hard, or it could be statistical. So basically, things that have kind of very bad sample complexity. So despite this kind of maybe looking a little bit a priori bleak, actually in practice the situation is quite different. So it's typically the case that very simple algorithms like gradient descent, maybe some simple Markov chains like Gibbs samplers, actually seem to do disproportionately well. And sort of the head scratcher here is, why does this actually happen? And the meta question here that we want to understand is, what makes a problem actually easy? And so one reason why answering this question is actually not easy is sort of this nice quote from Tolstoy, which is usually called the Anna Karenina principle, after the kind of introductory lines from Anna Karenina, which basically says that all happy families are alike and every unhappy family is unhappy in its own way. So basically what this means is that whenever you kind of get sort of tractable problems, they're sort of tractable for case-specific instances. And intractability is kind of ubiquitous, and we basically know why it crops up. So it's things like rich combinatorial structure, high-dimensional phenomena. And in contrast, whenever we sort of want to figure out why something actually ends up being tractable, it basically requires you to get your hands a little bit of dirty and actually mix a bit of theory and practice. And the end goal here that we want is to design algorithms that have some kind of provable guarantees. Of course, you might kind of ask the question, well, like how important is actually theory for these things? And I want to argue that actually this is quite important, and it's important for various reasons. So first of all, why does it actually matter to understand when problems are easy? So there's a couple of reasons. So let me give you a few. So maybe one is, while it's actually true that typically simple algorithms actually work quite well, oftentimes they have a lot of knobs or hyperparameters that one needs to tune. And sort of recently it's getting more and more kind of difficult to actually tune these things. And actually even the ways that do this are kind of increasingly more and more opaque, and even reproducibility is becoming an issue. And of course, from the point of view of science, sort of if we understand why problems are tractable, this will help us design kind of algorithms that are more principled and ultimately ones that kind of perform better. And of course, if we are able to understand what are the failure cases, then this kind of will allow us to be able to say when a particular algorithm ought to perform well. And finally, why is it important that you have guarantees? Well, it's important because there are oftentimes cases where actually kind of the algorithm sort of having some particular kind of provable performance is actually could be like a matter of life and death. So you can imagine that maybe you have some kind of self-driving car, and I'm sure all of you have heard of these instances of adversarial examples where if a sort of an algorithm is trained to maybe predict the speed limit, and if you sort of perturb the image ever so slightly such that it's kind of not like for a human it really doesn't make a difference, but the algorithm all of a sudden might think that the speed limit is something entirely different. And you can see that these are kind of instances where performance is actually a life or death kind of thing. So what's kind of the usual workflow that I like to do? So there's like a couple of stages. Just this is kind of like to give you a sense of what working with me might be like. So typically in the beginning, we would kind of identify some interesting phenomenon that we want to study, and this will kind of involve reading a bunch of papers, typically a mix of empirical and theoretical papers. And this is sort of the stage where you would typically sort of teach me some interesting things. After which we would kind of like to form some potential hypotheses that we want to test, and typically this will involve sort of setting up some controlled experiments, oftentimes designing some kind of clever setups to be able to sort of pin down more quantitatively some hypotheses that we maybe want to test, usually design a bunch of kind of synthetic experiments. And once we have a bit better of a sense of what's going on in these control settings, then we would devise some kind of mathematical formalization of the phenomenon we're trying to study and try to kind of prove and explain what might be going on. This part usually will involve a bunch of brainstorming, basically relating what we're observing to some known kind of models and results, and usually and hopefully learning some interesting new mathematics. And then after this, the end result is hopefully that we can design better algorithms than kind of like what people are already using. And this is the stage where we get to kind of give back to the practitioners. So this is kind of pretty short, but let me give you some sense of maybe kind of two representative problems of things that I'm interested in. So one will be in the context of this of inference, so basically sampling some distributions, and then the other one will be in this, I guess if there's time, maybe if not, I'll skip the second one, about sort of understanding some approximation aspects of flow models. So let me give you the first example. So this is in the setting which is pretty common. It's like a black box sampling setting. So you have some distribution which you're given up to some constant of proportionality. So it looks like p of x is proportional to e to the minus f of x. And you have gradient and value query access to the function f. And you would like to draw samples from this distribution. It may not be kind of quite apparent in this level of abstraction, but this is kind of it's a pretty ubiquitous setup. So if you have a trained model, checking the fit of the model kind of reduces to a problem that looks like this. And oftentimes, if you have a trained model and you want to use it, so maybe you have some model that takes in some kind of like a description of an images, and it needs to generate some images that match that some description, they pretty much fit exactly in this sort of abstraction that I had before. And much in the way that for optimization, you know that optimizing convex functions is easy, but non-convex ones is hard. There's also a dichotomy for this problem where f is convex. These are called log-concave distributions, and we know plenty of provable algorithms, but they're kind of restricted from a practical point of view because the distribution you can model are kind of unimodal. So they basically look like something like this. And of course, if you remove this, in general, the problem is just going to become hard. So as I said, intractability abounds. You're going to get sharply hard problems. And again, this kind of parallels what you have in optimization. Now the question is, can we go beyond this sort of setting of log concavity for things, for kind of assumptions on f that are of relevance in practice? So what can we do here? So one thing that we can handle is distributions that are multimodal but are sort of benignly so. So if you have a distribution that has a small number of modes and they're kind of similar in shape, then we can solve them in polynomial time. Then we can sample from this distribution in polynomial time. We can also handle another case of practical interest, which is when the distribution is concentrated near some manifold. So maybe you can imagine this is some lowish dimensional manifold of images or something. If this manifold has some nice geometric structure, if we needed something called a positive Ricci curvature, then again, we can sample from this distribution in polynomial time. And then I think I'm roughly out of time, right? Maybe like a minute.
No, you have more time.
I have more time? Okay, good.
You have till 1:45 since we were early.
Oh, okay. Okay, good. All right, perfect. Then I'll be earlier. But okay, so let me tell you about the second vignette. So the second vignette is about kind of understanding the approximation power of certain models. And this is going to be in this context of GANs and flow models. So in case some of you are not familiar, let me tell you a little bit what these flow models are. So this is kind of a hybrid model that tries to combine GANs with sort of standard likelihood training. So what this means is that you're going to assume that the generator that you would have like in a GAN-like setup is invertible. And if it's invertible, there's this kind of nice observation that you can write down the density of the push forward of the Gaussian through the generator G through basically the change of variables formula. So it might sound a little fancy. It's pretty simple. It basically just says that if you have some distribution, which you get by taking, let's say, a Gaussian and pushing it through some generator G, then you can write the density of this distribution at some point X as the density of the Gaussian at the pre-image multiplied by some correction factor, which is the determinant of the Jacobian of this map. So now that you have this, you have the likelihood for this distribution, so you can try to optimize it, and therefore you can just do basically gradient descent-like training. And of course, the rub here comes from the fact that calculating the determinant of a d by d matrix is in general going to be a d-cubed operation, which is way too expensive. So what typically people do here is they try to figure out families of kind of restricted architectures where you can evaluate these determinants in a more kind of efficient manner. So there's some pros and cons to these models as compared to GANs, and I'm going to focus on maybe what's the most important one. So the pros are basically that kind of like GANs, they've been scaled up enough that you can still get pretty kind of photorealistic image generation. Sampling is still easy because they're still parameterized as the push forward of some simple distribution like a Gaussian through a neural net, and because you have a likelihood-based training, the training is much simpler than it is for GANs. And also because you have likelihood, evaluating the model is sort of, again, kind of easier than it is for GANs. On the con side, what's the biggest problem is that these models are humongous. So in contrast to GANs, which sort of even a maybe moderately sized GAN can give you pretty good samples for, let's say, human faces, these models tend to be pretty huge. So I put some numbers here just for comparison. So GLOW, which is one of the state-of-the-art models for faces, was kind of trained for what's the equivalent of 40 GPUs for about a week, and it's about 1,200 layers deep. And so the question is, why do these models need to be so much larger than GANs to kind of get comparable looking samples? And there's kind of two hypotheses for why might this be the case. One is, as I said, because these Jacobians in the training need to be, these determinants of the Jacobians need to be efficiently evaluable, you can't kind of have arbitrary functions. So you need to restrict the architecture somewhat. And then you might kind of think that if the architecture is restricted, then the model needs to be kind of larger to account for that. The second kind of source of potential reason that the model needs to be larger is that because you're training with likelihood, this kind of corresponds to trying to match the input distribution in KL divergence, which is a pretty strong metric. And so people typically kind of abbreviate this by you cannot trade diversity for photorealism. And so you might need a bigger model for this reason. So basically, it's not kind of clear which one of these is the more serious issue, and it's actually not even more clear if this is more of a statistical or algorithmic issue. And so what we recently did was we tried to figure out what we can say about the first aspect, about representational issues. And so without kind of going too much into details, what we can say is sort of the following. So we can say that if basically there are distributions which you can write as kind of relatively small and shallow GANs, but actually you need a much deeper model to be able to approximate it if you're going to train an invertible flow-based model. And also, again, kind of not going to go too much into details, but some of the more common architectures, we also proved that there are very simple functions that these common architectures actually cannot even approximate. So even representational sort of questions end up being kind of problems in this picture. We don't really know how to say anything intelligent at this point about likelihood and sort of algorithmic issues, but that's for you, the next generation, to say something interesting about. So let me pause here if there are any questions. Okay, maybe I should just mention, yeah, I'm also taking 1 to 2 students, and if you're interested, please feel free to schedule a spot to meet with me next Friday.